All right, so number 1 said, or well, we've got to determine the domain, intercepts, vertical asymptotes, and behavior models, and the limits of each of the following. So, domain, x-intercept, y-intercept, vertical asymptote holes, and in behavior model, and the limits. As x approaches negative infinity, and as x approaches positive infinity. Okay, so first off, let's talk domain. Domain is everywhere except where the denominator is 0, and the denominator is 0 of both -4 and +3. So, all real numbers except -4, +3. X-intercepts occur when only the numerator is 0, so I see right now that x minus 3 actually cancels out from the top and the bottom. One of them does, leaving me with 2 in the numerator, which normally would make me think x-intercept, but that just means we have a hole in the graph at 3. So I'm going to go ahead and put 3 comma 0, because I know when I plug in 3 I get 0 still in the numerator. And then I get 7 in the denominator. So 0 divided by 7 would be 0. Okay? Now if I was sketching, I would remember that that bounce, or that multiplicity of 2, means a bounce. At the x-intercept, that is a hole in the graph. But anyway. So back to x-intercepts. X-intercepts occur when only the numerator is 0, so that would be at -5. Okay? Y-intercept is when x equals 0. So if I were to plug in x equals 0 into everything, go to the standard form, and I get -135 over -12, which simplifies to, no, you could just write, if you didn't have a calculator, then you could just write 0, -135 over 12. You know what I mean? But since we do have a calculator, I'm going to go ahead and type that in. -135 divided by 12. So -135 divided by, -12. Interesting, which makes that positive. Divided by -12, and you get 11.25. So, or you can write 0, 11.25. Okay, vertical asymptotes occur when the denominator and only the denominator is 0. So in that case, we're talking about -4. X equals -4. And in behavior model, so the higher degree is in the numerator, which means I'm going to have to do long division. I don't think I have enough room on there. Yeah, probably not. So I'm just going to go and do it here. So, divided into x to the 4th minus 4x cubed minus 18x squared plus 108x minus 135. Okay. So, what do I need to multiply x squared by to get x to the 4th? That is x squared. X squared times x squared is x to the 4th. X squared times x is x cubed. X squared times -12 is -12x squared. Change the sign. Minus, minus, plus. And I'm left with, those cancel out, I'm left with -5x cubed minus 6x squared plus 108x. So, what do you need to multiply x squared by to get -5x cubed? And that's a -5x. So -5x times x squared is -5x cubed. -5 times x is -5x squared. And that is a positive 60x. Okay. Change the sign. So plus, plus, minus. Those cancel out, and I'm left with a -x squared. 48x plus 48x minus 135. Although all I need is this last number, and I'm done. What do you need to multiply x squared by to get -x squared? And that is -1. So x squared minus 5x minus 1 is my behavior model. X squared minus 5x minus 1, which is a positive quadratic, right? Which means both end behaviors are positive infinity. Okay. All right. Number 2. I wish I had the foresight to write all these out before I started doing this. But oh well. Domain, x-intercept, y-intercept, vertical asymptote, whole, mean behavior model, and limits. You know what? In fact, I'm going to take a second and go ahead and do that. So if you just want to skip ahead until I'm ready to get back to them, feel free. Domain, x-intercept, y-intercept, vertical asymptote, whole, and behavior model, limit as you approach negative infinity, and limit as you approach positive infinity. Domain, x-intercept, y-intercepts, vertical asymptote, whole, and behavior model, limit as x approaches negative infinity, and limit as x approaches positive infinity. Domain, x-intercept, y-intercept, asymptote, whole, and behavior model, and okay, here we go. Number 2. Domain, everywhere except where the denominator is 0. And I see that the denominator is 0 at positive 7 and at negative 4/5. So those are out. Okay. X-intercepts, let's see if we can cancel anything out. I've got an x amount of 7 from the top and the bottom, leaving me 1 in the denominator, which means vertical asymptote. If you've got, if it makes the denominator 0, then and not the numerator, see it once I'm left at just 1, it just only makes the denominator 0, then you have a vertical asymptote. So 7, and while I'm here, I might as well go ahead and identify the other one, negative 4/5. Okay? X-intercept, however, is when just the numerator equals 0, so I'm thinking negative 2, 0. Y-intercept is when x equals 0, so if I plug in x equals 0, just to kind of show you what you're going to get. If you plug in 0, if you plug it in here, then you get 2 over negative 7, because that's not to the first power, right? 0 minus 7 is negative 7, and 5 times 0 is 0, and 0 plus 4 is 4. So you actually end up with 2 over negative 7 times 4, which simplifies down to 1 over negative 14. And if you were to divide this, 14 goes into 196 14 times. So negative 14 over 196 is in fact negative 1/14. So however you put it in standard form, you just plug it into what's left over. So negative 1/14, which is some decimal, some small decimal close to 0. Hole in the graph. There isn't one because the only thing that canceled out was left within the denominator, which made it a vertical asymptote. Okay. In behavior model, the higher power is in the denominator. If the higher power is in the denominator, that means automatically that the that there is a horizontal asymptote and it's at 0, which means both my limits are 0. Okay? All right. Let's go to number 3. Okay, this one's kind of an interesting one. I'm going to factor the denominator. So the denominator is 2x times x plus 4. So the domain is anything but where the denominator is 0, which is 0 and negative 4. So 0, oops, just kidding. Oh, forgot what I was doing. So all real numbers except 0 and negative 4. X-intercepts are where the numerator is 0, but before I do that, let's talk this real quick. You always need to see if there's anything that cancels out before you identify x-intercepts, and in fact the x's cancel out right here, which, and there's no other x left in the numerator or denominator as a factor by itself, which makes it a hole in the graph at 0. Now if I want to know what the hole in the graph is, then I plug in 0 into what's left over. But if you plug it in here, you get the square root of negative 16, which is imaginary. And if you try to plug it in here, you would get, again, well, you'd get 0 times an imaginary number divided by 0, which is indeterminate. So I don't think we actually have one. We'll come back to that. Okay. Oh, you know, domain is that easy when we're talking about those functions, but I gotta remember what I'm actually dealing with. Okay. My domain would be that if I was dealing with a normal function. But I'm not a normal rational function, I mean. So here's what I know. I know from the denominator that if they are in the domain, that x cannot equal 0 or -4. But I don't just have a rational function. I don't have a polynomial in the numerator. I have a square root in the numerator. And anytime you have a square root, the interior of the square root has to be positive or 0, which means we need to solve this inequality. So I'm going to add the 16 and divide by 9. And when I take the square root, that means x is going to be greater than or equal to 4/3, but less than or equal to -4/3. So x has got to be greater than or equal to 4/3, but less than or equal to -4/3, which means my domain is -infinity, -4/3, 4/3 to infinity. I can't include 0. Well, doesn't matter because it's not even there, which means, yeah, we definitely don't have a hole in the graph at 0. But I also can't equal -4, and -4 is on this side, so you've actually got a gap in your domain at -4, which means my domain is -infinity to -4. Pick back up at -4 and go to -4/3, which we can equal. Gap, pick up at 4/3, positive, and go to positive infinity. And there's my domain. Okay, so back to the hole in the graph. There would be a hole in the graph at 0 if it existed there, but it doesn't, so there you go. Okay. X-intercepts are when the numerator is 0. The numerator equals 0 at 0, but we already discussed that. And when this equals 0, which if you just trade that with an equal sign, then it would be plus and minus 4/3. So those are actually X-intercepts. -4/3 and +4/3. Okay. Y-intercept again is when x equals 0, so there isn't any. And go ahead and erase that to none. Vertical asymptotes occur when the denominator and only the denominator is 0, so -4, and it's in my domain, so -4 is a vertical asymptote. And the end behavior model. Okay, so this is kind of the interesting part. When you go to infinity, the terms that don't matter are like the 8x and the -16. You're multiplying these two, so those do matter. So what I'm going to deal with is I'm going to say I've got 4x times, basically I'm just dealing with this, right? Because the 16 doesn't matter. The square root of 9 is 3, and the square root of x squared is x, but it's going to be the absolute value of x because no matter what I plug in, I square it, and I take the square root, I get back to a positive, so I'm going to do that. Over 2x squared, right? So that means I basically have the same power on the top and the bottom. The only issue is, depending on which infinity you go to, I could end up with something else. So let's talk about it. When you go to positive infinity, that was always an easy one to start with. Go to positive infinity. If I plug in a billion, I've got basically 12 x times the absolute value of x over 2x squared, which simplifies down to 6, right? But when I plug in a billion times a billion, I get a billion squared. And I plug in a billion, I get a billion squared. These cancel each other out, something divided by itself is 1. So I'm just left with 6, right? When you go to negative infinity, you plug in a negative billion here, you get a negative billion times a positive billion. Because when you plug in a negative billion, it becomes the absolute value of it is positive. So you've got negative billion times a positive billion, which means it's a negative billion squared. When you plug in a negative billion here, you get a negative billion, and then you square it, you get a positive billion squared. Basically, what you're ending up with is a negative times a positive divided by a positive, which is negative. So it's actually -6, which means my horizontal asymptotes, +6 and -6, are my end behavior models. And there you go. You could have combined those. I just wrote them this one. Okay. Now again, remember you can graph that and make sure, but that is what it's going to look like. Okay. So let's talk about this one. Okay, I'm going to remember what I'm doing now when I do this. As far as domain goes, first you got to look at the numerator and look at the denominator. The numerator is a polynomial that has no domain issues itself. The denominator, however, is a logarithm, and anytime you have a logarithm, the interior, x plus 5, must be positive, right? Because logs only exist. You can't take the log of a negative or a negative number or 0. So x has to be actually greater than negative 5. So I know my domain is starting at negative 5 and it goes to infinity, right? The only issue is that you also have to deal with the fact that you have a fraction, right? So that was just me talking about natural log itself, right? If I gave you that function and I said, hey, what's the domain? You would say negative 5 to infinity. But now that it's also in the denominator of a function, you know that the whole thing, natural log of x plus 5, cannot equal 0. So you need to solve for the value that makes it 0 and exclude that. So I need to solve for x. I get x plus 5 cannot equal e to the 0, which is 1. Subtract 5, which means x cannot equal negative 4. Which means my domain is negative 5 to infinity, except there's a gap at negative 4. Okay? So my domain is negative 5 to negative 4, negative 4 to infinity. Okay? All right. Going through here, x-intercepts. I need to factor the numerator, so the factors of negative 42 that multiply to give me, or add to give me negative 11, 21, 2, let's see, 2 and 21, 3, and 7, 3, and 14. Yeah? Okay. So I'm thinking negative 14, positive 3. Negative 14, positive 3, but then divide by 2. Okay, x minus 7 and 2x plus 3 in the top. Okay, so my x-intercept, I've got a positive 7 and I've got a negative 3 halves. So both of those are in this domain, which means they're both x-intercepts. Positive 7 and negative 3 halves. Negative 3 halves is negative 1.5, which is somewhere in there. Okay. Y-intercept. Y-intercept is when x equals 0. So if I plug in x equals 0, you get negative 21 in the numerator. And when you plug in 0 in the denominator, you get natural log of 5. So whatever that is. You could just write that. 0, comma, negative 21 over the natural log of 5. Or you could type it in and see what you get. Negative 21 divided by the natural log of 5. And negative 13.048. Or 0, negative 13.048. Okay? Vertical asymptote. So vertical asymptotes occur when the denominator and only the denominator equals 0. So I know the denominator equals 0 at negative 4. I'm actually curious about whether it's also negative 5. I want to test it right quick. So 2x squared minus 11x minus 21 divided by natural log of x plus 5. Interesting. Okay, I'm going to approach negative 5 from the left. So negative 4.5, negative 4.9, negative 4.99, negative 4. Interesting. So it's actually getting smaller. Doesn't look like it's a vertical asymptote, is it? I don't think so. Okay. That's what I was going to say. I think if it's in the numerator, it would be a vertical asymptote, but since it's in the denominator, it's not. So vertical asymptote, x equals negative 4. That's when the denominator is 0. Okay. Hole in the graph, there isn't one. There's no common factor in the numerator and denominator. And in behavior model. Well, let's talk about in behavior in general. You don't go to the left. So there is no in behavior to the left. As far as going to the right, you got to think about the most powerful term. The numerator is a positive quadratic and the denominator is a logarithm. A quadratic is much more powerful than a logarithm, which means to me that I'm basically dealing with, to the right, 2x squared, the most powerful term in the denominator, divided by natural log of x plus 5. So if you plug in like a billion, 2 times a billion squared is huge, and then a natural log of a billion plus 5 is actually not that very large, which means we're going up to infinity, because that's just a really large positive number divided by another positive number, which means we're going to infinity. So I guess my end behavior model would be that, in essence, 2x squared divided by the natural log of x plus 5. That's not a perfect end behavior model, but it does tell me what I'm going to on the right-hand side. Okay? Okay, number 5. So let's talk individual functions. 6 minus 3 times 4 to the x is it's an exponential function. It has no domain issues on its own, so I don't really have to worry about that. And then 10 plus the square root of x squared, which is also interesting. So as far as a function goes, right, x squared, anything inside a square root has to be greater than or equal to 0. But if you take the square root, you get positive and negative 0. So, I mean, they'd be like saying this: x has to be greater than or equal to 0 and less than or equal to 0. You have identified that x can be anything. Because literally anything I can plug in there, I get a real number, right? Negative 42 squared. Positive, take the square root of 42, right? So nothing is an issue, except for the fact that, okay, so individually they have no domain issues, but I do have a fraction, which means the denominator cannot equal 0, right? Which means the square root of x squared cannot equal negative 10. Get rid of the square root by squaring. X squared cannot equal 100. Negative 10 squared is 100. And then x cannot equal either, in fact, when you take the square root, positive or negative 10. So both positive 10 and negative 10 would create a domain issue, which means my domain is everything except positive and negative 10. All right, x-intercepts. X-intercepts occur when just the numerator is 0, so I'm going to set the numerator equal to 0. 6 minus 3 times 4 to the x equals 0. I'm going to subtract 6 over, divide by negative 3. And I'm going to take the log base 4 of both sides. The inverse of the exponential base 4 is the log base 4. And so I've got x equals log base 4 of 2, right? Now, I could have solved this another way, because, I mean, you could say log base 4 of 2, but if you think about it, 4 to the x equals 2, well, that's just 2 squared. So 2 to the 2x equals 2 to the first. That's getting, which means when 2x equals 1, which means x equals 1/2. So my x-intercept is 1/2. But if you're at log base 4 of 2, you wouldn't be wrong. But it is 1/2, 0. Okay. Y-intercept. Y-intercept occurs when x equals 0. So when x equals 0, let's plug that in. I've got 6 minus 3 times 4 to the 0 power divided by 10 plus 0. 4 to the 0 power is 1, so I've got 6 minus 3 in the numerator and 10 in the denominator, so my y-intercept is 3/10. Okay. Vertical asymptote occurs when the denominator and only the denominator equals 0, and we already found that the denominator is 0 at both positive and negative 10. So both of those are vertical asymptotes. Holes in the graph occur when numerator and denominator are 0, and that does not occur, so we have none. And in behavior model. Well, let's talk in behavior in general, right? So let's talk positive infinity, negative infinity, most powerful terms. When you go to positive infinity, this term is very large, 4 to the infinity power, although it is a negative 3, right? So negative 3 times 4 to the billionth power is a very large negative number, whereas this right here is just, I mean, if you plug in a billion, you get a billion, right? So what I get is this is more powerful, which would make me think I'm going to infinity because this is more powerful, we're going up, right? But divided by a negative, that means I'm actually going to negative infinity to the right, which is interesting. Okay, now let's go to negative infinity. Let's plug in a negative billion. When you plug in a negative billion right here, 4 to the negative billionth power is actually very, very small. So 4 to the negative billionth power is basically 0, which means 6 minus 3 times 0 is just 6 in the top. So I've got 6 in the top. And then in the denominator, when you plug in a negative billion, you get 10 plus a negative billion squared is a positive billion squared, and the square root you get a positive billion. So 10 plus a billion is huge. So that means we're going to 0. Okay? So as far as end behavior models go, on the left-hand side, you've got a horizontal asymptote. And on the right-hand side, it's not a horizontal asymptote. It's just negative 3 times 4 to the x over basically the square root of x squared, or just the opposite value of x. I'm not going to be looking for end behavior models like that. So on your test, it might be a multiple choice option. It might be just like determine if you have a horizontal asymptote or not. It might just be determine the limits, but I'm not going to ask you to figure all that out, okay? Or to tell me that. I would expect you to be able to get to that and understand where you're going, but anyway. Okay, number 6. So, domain. This is an exponential function. They have no domain issues. This is an exponential function. They have no domain issues, which means the only domain issue I have is when the denominator itself equals 0. So I'm going to set 6 minus 10 to the x equal to 0 and solve. So I'm going to go ahead and subtract 6, divide by a negative, so they're both positive, and then the inverse of the exponential base 10 is a log base 10. So x cannot equal log base 10 of 6, or just log of 6. So my domain is all real numbers except log of 6. Okay. X-intercept when the numerator equals 0. So 5 times 10 to the x minus 9 equals 0. Please be aware that you cannot multiply 5 and 10. It's not 50 to the x. That's a completely different expression. 5 times 10 to the x and 50 to the x. Not the same thing, okay? So I'm going to add 9 over. I'm going to divide by 5. And again, the inverse of the exponential base 10 is a log base 10. So that's an understood base 10 log of 9/5. So, just kidding. I'm going to turn that to a log. Log of 9/5 comma 0. Alright, y-intercept occurs when x equals 0. So when x equals 0, you get 5 times 10 to the 0 minus 9 over 6 minus 10 to the 0. And 10 to the 0 is 1, so that is 5 times 1, which is 5. You get 5 minus 9 over 6 minus 1, so that is negative 4 over 5. Okay. Vertical asymptote is when the denominator is 0, and that we already solved. It's log of 6. There's no hole in the graph because there's no place where the numerator and denominator both equal 0. So none. And in behavior model. So in order to figure out that, I'm gonna have to plug in numbers approaching it, right? The infinities. So if you plug in a billion, if you go to positive infinity, these exponential functions are way more powerful. So I'm basically dealing with 5 times 10 to the x over negative 10 to the x, right? In fact, they're growing at the same rate, which means this is negative 1 times 10 to the x. When you plug in a billion, 10 to the billionth divided by 10 to the billionth is just 1. Bring that up so you can see it better. Which means I'm really just dealing with -5. So when I go to positive infinity, I'm going to -5, which makes it a horizontal asymptote. But when I go to negative infinity, when you go to negative infinity, 10 to the x is approaching 0, which makes the most powerful term in the numerator -9. And when you approach negative infinity, this is also going to 0, which makes the most powerful term in the denominator 6, which makes that -3/2. So I actually have two horizontal asymptotes, -5 and -3/2. Okay? So that is the front page. I'm going to make a separate video for the second part.